Start recording. Alright, so where we left off... I hope I'm running the right thing. I am running the right thing. Okay, so where we left off, we've got this sort of thing going. If we hit space, we get some separation. But I think, as you can see, there's a bug. Because they shouldn't both be moving in the same direction, and it's kind of tricky to trigger. But yeah, they both move at the same time. So something's gone horribly wrong. And so what we're going to do today is try and track that bug down.
Okay. Yeah, my guess before was like it's like an early out type of thing. Like if we didn't stop looking for intersections, then maybe they both have a chance to be the winner, and if they both are, maybe they both separate. But yeah, I had no idea what it was.
Well,
I don't think I've ever got. Oh, there it is. Okay.
Yeah. It's not a bad guess. So we know that the problem is happening when we do the separation. So, we hit space and something goes wrong. So it's like, all right, well, the update method, we hit space, that just calls do separation. And what we can say about do separation pretty much immediately is that it is a it's one of these awful methods that have do on the front, and that kind of just it's a bit tricky to explain exactly why this is, but that's just asking for trouble. You're mutating the state of something.
You're not passing it in. You're doing it in some hidden black box.
Exactly, and it's also the case that this is not particularly easy to test. It's like, all right, we have two triangles, and maybe they're going to separate badly, incorrectly. Those ones seemed okay. Yeah, when you want it to trigger, it doesn't trigger. But once you do that separation, you've lost your testing data. And so this is something we want to try and avoid. We want to make sure that this doesn't mutate state. So what we're going to do is we're going to take a little plunge into sort of functional programming land, where this is sort of just a function that you apply to things. So and the simple way we're going to do that is stick static on it, and then watch all the errors show up. And basically, this is going to tell us very quickly, what do we need to pass into this method to make it do the thing. So, yes, we need the shape list and the shape count. Do I have a bug already? Yes, there we go. Shape count. Okay, now we have this pending separation, and that's kind of like an output, because what we're doing here is we're actually modifying some of our input data. So we might cut off here. And so we just want to output pending separation, then we'll worry about this stuff later. So
although I assume we don't want to output. Oh, you're not putting any. You're actually passing it in. I was going to say, if you were going to output it, we don't probably want to allocate it again. We might want to return a vector 2 star.
Well, the thing is, you can't return something that you've allocated on the stack.
Oh, right, because you're talking about the locality of it before.
Yes, so once you pop up the next level on the stack, that suddenly becomes memory that might get overwritten by a different function call.
Fair enough.
So what we'll do here is we'll take our we'll just pass in pending separation. And Yeah, this is the only bit of code in here. I mean, we can go through and we can check to be sure, but just to skip us ahead a bit, this is the only bit of code that actually does, I guess, something.
Well, this does something. What do you mean? Well, this mutates the pending separation, right?
Yes, but whereas this one mutates the positions of the shape. So what we could do, you know.
Oh, I see. That's the do separation part. This is the prepared data. Sorry.
I'm
talking over you.
No. It sounds like you've got got exactly right. Like if we didn't care about this, if we were like, oh yeah, sure, this method's going to mutate a list of shapes, we don't even have to pass this in. We could in fact stack allocate this in the do separation method, but because we actually want to know the separations outside of this method, for reasons that will become clear fairly soon, we'll take that bit out and we'll just stick it down under here. And so now all we have to do is pass in our arguments, shape, count, pending separation. So now this method, it doesn't mutate anything, so we can call it something else, like calculate separation.
Well, I don't know. It's semantics probably, but it is mutating the pending separation array.
Yeah, so it's like this is an input, this is an input, these are immutable, this is a output, I guess. And yeah, it is mutating that, but in most normal...
Using it as like a... Are we using it like a working buffer or not really? Because there's stuff kind of in there that's going to stick around, or are we clearing it at the beginning? I can't remember.
It's very much like if we had a method like void foo out in bar. It's very much like a method like this. It's like an out parameter, but
yeah,
it's got a different pattern of allocation to it.
So one more question for me is like, why are we? I can't quite. So we're gonna calculate on the pending separate. We're gonna calculate. We're passing this in as a kind of a working buffer. Then after we've got our data for the separation, we apply it to the positions of the shapes, and then we clear the pending separation. But I mean, this is probably an easy or just a convention thing. But like, why aren't we clearing it before we do the calc? Because does it matter at all, or did you do this deliberately?
No. So now that we've done that, we could do this. What we could also do, and maybe this is worth doing, is we could go ahead and we could do a bit of revision from last time and do something along the lines of vector2 pointer pending separation equals stack alloc vector2 shape count, and just stick it on the stack. Now, of course, to do that, we'll have to get rid of this pending separation up here. But this is actually not bad because this gets rid of some things, and we have to go and safe block.
Yeah, I thought we were going to use it outside the method, but if we're not using it outside of it.
Well, basically we're making our code more functional in sort of a functional programming sense. I'll do the same thing here. So we do need to clear this, and I think we might have talked about this. In the previous stream, and that is that stack alloc isn't guaranteed by the specification to clear the memory that it gives us, even though in the version of .NET we're using, I think it does. It is possible that what we get back here is just garbage memory. So we do need to clear it. Now array.clear is not going to do the trick, obviously, because it doesn't take a pointer. What we would really like to do is just call memset on the buffer. but off the top of my head, I don't know a sensible way to do that without importing it from the C standard library using interop. So you'll recall that in the River City code we do this, we call memset, and I think we looked at that last time.
Yeah, I remember. I found that pretty interesting.
Mm-hmm. So yeah, so we still have to do this clear first, but that's fine. Calculate separation. So now, yeah, we'll turn that into a pointer. Where did the code go? I'm not sure we even actually have to change anything here. I think it's all just going to work. Yeah. So simple as that. So what we can now do with this is like the clever part, is we can take this code here and we can go down to our draw method, and we can sort of, roughly speaking, we just sort of paste it in. Let's leave it commented out for now. And let's take our shape drawing code. I guess, yeah, we need a scope for this actually. Yeah, we can actually uncomment that. Okay, and so what we have here is we have a bunch of shapes and a bunch of pending separations. And so if we now go for each shape, draw the shape in its new position, we can do that. So rather than this loop here, we'll use this one here, and everywhere we look at shape position, we go shape position plus pending separation I.
I think I lost you now.
Sorry?
You moved. Sorry, I just think I just kind of lost you.
Okay.
So wait. So
so
there's the first loop.
I've
That doesn't.
Yeah, I've copied this loop into.
Oh, I see.
Into here, and I've replaced the one that actually applies the pending separation. So I've gotten rid of this entire loop because this is the one we want.
No, I don't know. Oh, sorry. I'm looking at this. Just there's that. This is gone. And
Yeah. Now you're good. Now you're good.
Shape position plus. I think.
So yeah, everywhere that I'm looking at the shape position, I'm just like, all right, give me the shape position plus the pending separation.
Want to change the color, maybe?
Yes.
What is this complaining about? Oh, just the unsafe bit again.
Yes, I think it's just unsafe.
Yep.
Too easy. So, and then what we can do, just to like really drive the point home, is we can actually copy this. I know we just got rid of that loop, but we'll bring it back. We can do line batch dot arrow from shape dot position, shape I dot position, shapes I dot position to shapes I dot position plus pending separation. So this is just drawing the arrow that is the pending separation. And then what have we got? 10f divided by zoom, thickness. And turn. Let's just give these a bit of alpha so they don't blend in too much.
This whole doing math in the draw loop is freaking me out, but only because I've kind of trained not to. But I know this is just for debug, so.
Well, I mean, it's kind of like we were talking about the other day. So when you are fetching stuff, like, I mean, obviously this is like a really simplified program, so it's not a big deal. But in a real program, when you fetch stuff from, say, L2 cache, I think we said you had about 200 cycles waiting for that data to come in. Maybe less if it's like prefetching nicely and so on. So those 200 cycles, you may as well be doing maths in those cycles if you have some maths to do. Like it's better to be, I guess, it's better to grab some stuff out of the cache and do some maths in the background rather than pre-calculate everything in an update loop and then have to get double the amount of data out of a cache, for example. Does that make sense?
Yeah, I think that's going to be something I have to really practice to get a feel for like that. Well, I mean, I don't actually. So you say 200 cycles, but I don't know if that's like, well, if I had 201 shapes, I'd be guaranteed to get out of that limit.
I'm talking like 200 cycles per cache line, very roughly speaking. And cycles would mean CPU cycles. So that's the. Let's see if I can bring it up. If we look at the Intel Intrinsics Guide, for example, and bring up, say, come and load, MMQRT, PS. So, like, these ones, latency 13 cycles. So that's 13 CPU clock cycles. It takes 3 cycles if you're just shoving a whole lot of these in a row. Every 3 cycles you get a result back, whereas something like ridiculously fast, like add, that takes 1 cycle, although there's 3 cycles between when you issue the instruction and when the instruction comes back, before you can get the result.
2 additional cycles at the end.
So, well, you can
get everything.
You can imagine if you have like add something, then add something to that, then add something to that, then add something to that, then add something to that. All of those are dependent on each other. So you can imagine that takes 3 cycles. But whereas if you have like add something completely unrelated to something completely unrelated, add some unrelated things, unrelated things, and you interleaved them that way, which the CPU can do automatically, then you can issue 1 addition per instruction on Broadwell, for example. So basically, the conclusion of that is that you have 200 cycles, which means you can issue roughly 200 additions, let's say, for a single memory fetch from L2 cache. And those things will balance each other out. It's like, while you're waiting for that data to come in, you may as well do 200 additions, or was it like 66 additions if they all are interrelated, or what was it? Square root was like 15 cycles or so. So you could do you could do, let's say, 20 odd square roots, for example. So that's the sort of headroom you have if you're coming from L2. If you're coming from L1, then it's a bit different because that's like 3 cycles to fetch each piece of data. So anyway, that's sort of roughly what I mean by cycles. So the point is, like, just from a performance perspective, it's not a big deal to be doing maths in draw encode. The other thought is, like, there's no point in like doing the maths in update and then saving the data, then loading the stuff in draw and just drawing it. You may as well just calculate it in draw. There's really nothing that special about draw. Like, it does depend on how your game is doing its timing, to line up to frame boundaries. So maybe you have like specific frame requirement, like frame time requirements for draw, but that's kind of unusual. Another way to think about it is, I know you've been looking a little bit at the ImGUI stuff, and I have as well. And the way that works is you're like up here in update, and you're like, we'd be like, where's update? You might be like, ImGUI button, there. You might have this code here, and what this is going to do is it's going to stick some vertices into a vertex list. it doesn't really matter if you're sticking vertices into a list of vertices to send to the GPU in update or you're sticking them in draw. There's like kind of no difference between those two things.
I thought, yeah, my head's spinning because I remember like having to change a lot of draw methods in River City. It could have been for a different rule violation, but I was, trying to keep, I ended up moving a lot of game state out of there and into, like storage variables on the class. But, I thought that there was a difference because in update and draw, that especially if you're not like vsynced or whatever, you're going to, potentially draw's going to get called more often than update. But I guess that's also a concern.
Well,
Not a
actually,
concern if you're mutating state. Only a concern if you're mutating state.
it's actually the other way around, I think. Maybe you have that backwards.
Oh, probably.
So, I mean, it can be either way. So you are if you are running late, I guess, like if your simulation is dropping frames, you might not call draw, but you kind of have to call update. So draw might not get called. So
Right.
basically,
That's
you never want to mutate stuff in draw.
Yes.
On the other hand, your simulation might be paused, for example, and you're going to be calling draw again and again and again, perhaps because you're drawing like an overlay over the top or something that has
Yeah,
user
that's
stuff.
right.
So
Okay, so like when you're doing math in the draw method, it's like, again, have to think about it from a purely functional mindset where it's like anything that I can do in here that I think I can get away with from the cache point of view, anything I do in here has got to be throwaway. I can't store this anywhere.
exactly, that's pretty much exactly the way to think about it. It's like it's really unusual the case where you would be mutating stuff in here. Like maybe I think the only reason you mutate stuff is if you're like counting frames or something. Or you're storing like drawing specific stuff. It's like every other frame we ping pong from this texture or something.
Yeah, I can't imagine. Like I don't think I'm that terrible that I would actually like purposefully mutate state and draw, especially when I know that the number it's not going to be lockstep necessarily with updates. So I don't know
Yeah.
why I would have done that, but I'm having a hard time. I mean, it was 5 years ago, so
Yeah.
I don't really remember why I had all that rework to do. But I think it had to do with the very clunky UI stuff, and I think I was probably accidentally just mutating UI variables
the
inside
UI.
draw.
Yeah. I think that must have been what it was. So the UI got a little bit confused between what was like I guess called from drawing stuff locally, and then there was a network issue. So it was a bit more complicated than just draw update. But
No, that's
yeah,
right. Yeah, there was the networking stack. Although I don't know if we did the menus again, I'd probably just find a way to skin ImGUI.
that's not an unreasonable idea. I think part of the issue is that a lot of our UI was actually networked in various ways
Yeah,
for
pretty much
reasons
all of
that
it.
are annoying. So that would be tricky. Anyway, so just to finish up here, do you want to just change the color of that one because that
Royal Blue.
that will come out nicely colored, and I think all this code is correct.
Okay, whoops. So you got 03. Okay, so this one's you've got 06.
Yeah, so
03.
the only other thing is these ones you want pending separation as well.
From and to, yeah. Okay. Boom.
So we're basically drawing where the shape's going to end up. So this has a nice property that we get to calculate separation without losing our input data. So it's kind of like, and if people watching at home will know about the River City Ransom underground videos.
Whoops. What did I do here?
Oh,
I
that's
drew
pretty
over
good,
top.
actually. Well, if you do them, that they have some separation, so you can see on my screen at least, there's your bug. We now have a reproduce, and I mean that's a bug too because they're both moving in the same direction. So we now have a reproducible case of the bug.
But I screwed up my arrow though. My arrow doesn't look cool at all.
Well, that's just because it's really, really short. I think if you land on another example where it's
I'm gonna try to reproduce yours. Oops, that's not.
That's all right. So anyway, what I was going to say is like people who've watched the Underground series, and you will certainly know that on River City we had a kind of a similar thing where we could take. There you go.
Yep.
We could take snapshots of the game state and play them back.
Yeah.
And like you would not believe how much debug time we saved by having that mechanism there.
Yeah, I think I mentioned at least a dozen times how that was probably it was necessary to have that. I don't know how you could make a game without that.
Well,
at least one with a deadline. Well, yeah, but they may not have
well, often those games are really buggy, or they're really simple. Like our game was it was a little bit buggy, let's be honest, but it was extremely complicated. So if you don't have that, there's like a limit to how much complexity you can add.
Yeah, and there's always a trade-off between how much, there's always a scheduled trade-off in a commercial product with how much time you have and when you're going to have to stop. And But yeah, I'd say the loop recorder bought us an insane amount of time. It's too bad that's not something that you can kind of generalize. Like I think every game probably has to have its own version of that, but there must be. It's just too bad it's not kind of square one. I don't know if people who make Unity games, if they can kind of maybe Unity has this built in. You kind of have to follow their rules and then you get that at the end, but I don't actually know.
Well, I mean, you'd hope so with Unity because I mean they could do it. The interesting thing is the way that Casey does it is he just sucks out all of the memory of the process and just dumps that to disk. So while we had the network serializer, so we had a snapshot that's a couple of kilobytes. This is there's a gigabyte per snapshot. So we did have the nice property that we could send those on email easily.
Yeah, or just drag and drop into Slack. Wait 2 minutes. Oh yeah.
Yep, found the bug. So yeah, cannot be understated how important it is to be able to basically replay your input data when you're hunting down bugs. This bug would be such a pain in the ass to do unless we did something like a snapshot system or like this thing. We've done this functional system where we get to run it, but we also get to keep our input data and we just keep running it. So what we can do now, we've confirmed there's a bug. We've actually cleaned up our code a bit. This code is just straight up nicer. And now all we have to do is we just go into the debugger and we're just going to set a breakpoint on calculate separation, and we can now just we can do the debugging thing. I don't think we've ever really done this on stream.
No, I don't have edit and continue on my side.
Oh no, you don't need edit and continue. You just need the debugger. So did you close? Oh no, you're still running. Good.
Yeah. Good.
Sweet. Okay, so now we don't actually have to step through this. So what we do first is just get a feel for what the bug could be, because it's kind of the case that any serious bug, this is not a particularly serious bug, but any serious bug, I guess, could be in a lot of places, and you want to narrow down quickly on what that bug might be. And the way to do that is sort of start at a really high level and just spend some time thinking about the problem. And it really helps to understand what your code's doing as well. And so that sort of makes the bug easy to find. So let's just go through this now. We allocate stuff on the stack. Just get my window out of the way as well. Okay. Step into. Okay, so we allocate some stuff on the stack. That's straightforward enough. I think we know that, we're assigning stuff to these axes. It's like, all right, we get here and we're like, okay, so we have some get axes methods. We get circle axes and get polygon axes. So we just sort of make a mental note. And I mean, you could write this stuff down if it's a particularly hairy bit of code that's got the bug and you don't know where it is. Maybe start writing things down. Well, it could be the axes. We'll keep going. It's like, okay, distance squared, combined radius. Oh, this is just skipping stuff over. We're not having a problem here with like, oh, it's not detecting intersections. So we can kind of safely say it's probably not that code. It could be the axis, maybe the axis is wrong, but these arrows look pretty good. So it might not be the axis, but we know that there's some code we haven't dived into in these methods. Separation axis. So we're going through here and we're doing project onto axis. So it's like, well, maybe the projection onto the axis is wrong. Although, again, we look at this, it's like, well, they're separating correctly relative to each other, but, so maybe that's worth looking at. And then what else have we got? We've got the overlap calculation. So this is like, all right, well, we've done the projection. Do they overlap? This is something we tested this pretty thoroughly last time, so it might not be the problem, but it's handy to keep in mind. The separations, they are correct relative to each other, so who knows? Keep going, and then we get, okay, we've detected intersection. If did intersect, get mass, and then we're moving by some, multiple of the mass. It's like, that's new code. And I say new code, I know it's been a little while since we actually wrote this at this point. But this is the stuff we just added, was this mass for polygons. You'll recall we wrote, get area over polygon. So just by going through this calculate separations method, we've said, okay, here's all the places it could be. Let's start at the most likely place, which is going to be get mass. Oh no, I've lost the... Hello? Are you still there? Mm-hmm. I've lost your screen. Oh, there it comes. All right.
Just a momentary internet bubble.
Yeah, just blame Google for that. Okay. So...
Just so I'm clear, I mean, I didn't expect to see the bug is that there's two separations happening. We're expecting two of them. We're expecting one of them to happen. Isn't that right?
No, I mean, we apply pending separation to both A and B, so both shapes should have some separation, but
right, because of the toy mass thing, they're both kind of being moved in a small amount, but the fact is that they end up going in the same direction.
Yeah, so you'd expect them to separate in opposite directions, I guess. And so we can kind of say, hopefully, I kind of just barreled through that, but hopefully sort of the concept there makes sense, is the fact that you walk through the code, make a note of all of the little branches on the tree that you haven't stepped into. So, we haven't examined that thoroughly. And then you kind of well, this seems the most likely culprit, so we'll start with that possible branch. So we're kind of doing a, what would you call that? Like a depth first search. Because the bug is most likely to be one of the leaves. And so it's good if we can say, well, it's probably not get axes. That's a whole lot of debugging we don't have to do.
And we've been using that forever.
Yeah, so that's kind of the theory, and I mean you can do that very quickly. So this is where I'm gonna hand it over to you.
No,
don't worry, it's not too hairy. And I'm gonna say, right, here's a bug. This is quite a simple bug, and hopefully you have a rough idea of what the process is. So I'm gonna leave this with you and sort of walk me through your process of tracking down what this bug is.
No. But I will try.
Give it a go.
I don't know. Yeah, I mean, I was kind of weak on this before, but
we will make you stronger.
All right, so so clearly we intersect, get the mass of A and B. Looking at the mass values for funsies.
So
Um,
I mean that's a smart thing to do. Like,
B has a negative.
sorry, I've lost audio just now. Do you want to start
Oh,
again? Say that again.
I'm just looking at well, B has a negative mass.
I think we found the bug.
Yeah, I mean, I'd like to have a negative mass. Unfortunately, some things just aren't meant to be. So, all right. So this is the leaf. Um,
So we can step into and we can step into the get mass specifically for B. Um, so looking at the values and just sanity checking them is a good technique.
yeah, well, that jumped up. So I'm just gonna kick up another cycle. We'll go into B. So what's the problem here? So we have yeah, 3 vertices and so is this gonna be one of those math abs type of things? The shape. So we're going from negative 82, 101 to 82, 101. That seems suspicious too. But no, that's fine. Okay, so
So
algebraically optimize this.
the reason that these are like mirror opposites of each other is because they're relative to the center. So we recall how we built this thing. It's like
Yeah,
with a
I
radius.
vaguely recalled that, and then I realized that wasn't suspect at all because I got confused by that last time, and I'm like, how did you get that perpendicular line? Yeah. Um. Okay, so width is 2.x minus from dot y. So negative width is not a thing. So this is one of those things I think like because I'm not mathy, I'm not strong in math yet. This is the kind of thing I'd be like, well, maybe it needs to be absolute because I'm dealing with like a negative number that I don't think should be negative, but I don't think I can reliably flip the um, operators around or whatever they're called, the operands. Um, it's probably wrong, but this one is from and to, and this is to and from. So it kind of makes me feel like I could just flip them, but um, I'm not
Well,
sure.
what I will say is, I would try and because I know you actually do this quite a bit, and what I would say is try and avoid the temptation to stick an abs around things.
Yeah, it's kind
Because
of my bag.
unless you like know that's what you want, that's probably not what you want. So you could flip those things around. Um, I'll just say what it does help, and you'll recall how our algorithm works, is it basically takes segments of a shape. Um, if this is our polygon, and it's like, all right, give me there to there. So what we're doing is taking the width there, and then we're taking the average height. So this is the how we're getting the height is we're averaging between that point and that point to get a height. This is why there's a that plus that divided by 2 gives us height.
Right.
Whereas the width is just a straight up, that minus that. So if you flip the operands around, in the case where we've got the mass correct, you will actually just end up with a negatively sized polygon. So that's not great. So you recall the way this kind of works is it's like this one and this one are going to be positive, but this one at the bottom coming the other way is going to be negative, and this area here it's positive for the red ones but negative for the blue ones, so all you're left with is the positive area here, which gives us the total area of the polygon. So just switching those 2 operands around will just flip the area of the thing, because the red will become negative and the blue will become positive.
Yeah.
So that's the math side of that. So unfortunately, can't watch your screen when I draw stuff. So how did we go over here?
Oh, I don't know what's happening anymore. I was looking. I did the flippity dude thing, but I didn't. Just as you were describing it, I did it and it didn't do anything because, like you said, it just transposed the thing. But that means there's really not much left except this guy.
Okay, so this is the part in the debugging. We've narrowed it down to like 3 lines. And
Yeah.
the only thing we can say about this is, I guess, really pay attention. And be suspicious of like every little thing here. Because once you've narrowed it down this far, we could say, is our loop correct? Are we touching all the vertices? It's like, yeah, okay, we've got the count. All right, look at this one really carefully. So from is this one, to is this one. Is this going to get the subsequent vertices? Is it going to do the loop around properly? And I'll just tell you straight up, yes, it is. So we looked at these two and be like, we're absolutely sure that's correct. Let's look at this, and it's like, this is probably where the error is, because this is where we're doing some actual maths. So then we just like stare at that really hard, and it's like, well, what mistakes have we made here?
So the order. Well, I mean, I don't. Yeah, I mean, if either one of these is going, like, the thing that bothers me, if either one is negative, we're definitely going to get a negative, and we can't have a negative area. But
well, I mean, we can have a negative width times height. We can actually have a negative width, but we actually want a negative width. Is the point? We actually, yeah. So that's actually valid. What I will suggest is read the code, like maybe even read it out loud. Just read this block of code and see if you can figure out the error from that. That might be a useful way to try this. So off you go.
Let width equal the vertex. Let width equal the x component of the destination vertex minus the y component of the source vertex. Semicolon. No, I don't know. Like, it doesn't. I don't know if that's gonna help me particularly because I don't have the foundation. I'm still trying to pick this up piecemeal. Because I mean, what you described on what you just drew on the little whiteboard for for height seems like you said we're getting the average.
So we ignore this line and that line, those 2 green lines. We're just going to look at that one green line up here, and this is the line we're considering. And the way we're going to consider it is we want the width and the height. So we take the height, and there's like an imaginary, origin line like here, perhaps. Actually, no. The whole point of this, is that imaginary line should go through 0, which is going to be here, and then the x can be wherever.
But we're talking about one line. So which one? So when you say that really thick green line, which one is that? Is that from and to are the vertices?
So
that's the beginning and end of the line.
We know. Okay, exactly. So this is going to be from.
Yeah.
And this is going to be to. And if you're struggling with debugging, this is like drawing it out can also be helpful. And we know that this is from and to because we know we've specified the winding order last time. So we know we're going around clockwise, and this particular line is, that's the order clockwise. And and we can check from is n, and to is n plus 1.
Plus 1.
So we have that. We're quite happy with that. So height is going to be the y component of this
Plus
so
the y component.
plus
Yeah,
the y
this is,
component of this.
that's
And if
just
you,
the vertex math, and then you're cutting them in half.
and if you add those two together, take that up here. And this is like a simple average. You end up with this point here in the center.
Okay, so I don't think I'm not unhappy with H at this point. Like, I don't see any reason.
Yeah, and yeah, so and then that triangle's the same. So that triangle we get the area of this thing, at least the H component. So let's have a look at the W component. So the way you get W is like, all right, we have. Let's use a different color for this.
The W is simple, isn't it? It's just 2 minus from.
Yeah, so we have.
Oh my god, it's got a Y on it instead of a freaking.
Nailed it.
There. Oh, you were right. I like gave up too easily there when I was reading it.
It's really easy
right
to do.
There.
And this is kind of what I wanted to point out. It's like this is a sort of bug that happens. That's the sort of bug you need to be able to track down. And this is why you have to like really understand what the maths is doing and have a very good working familiarity with like what does that mean. And then you just have to be able to walk through it like really slowly.
Yeah, that was like the gorilla video. I'm like, that's an X, that's an X,
Yes.
that's an X. No, it's not.
Yes, that is actually really exactly what it is. And it's like, if you have to rewatch that, it's like something's wrong in this video. Geez, I better rewatch it again and again until I like watch it from a different mental perspective and nail that thing. So stepping out of your perspective like that is really helpful. And you can see already. So ta-da! Look, it looks like we've now got it correct. And the one with the smaller mass, effectively, is the one getting chucked off to the side. So we've nailed that bug. And so I think we might leave it there for now. But hopefully that was enlightening.
I can't. No, this is like Fruit of the Loom had a cornucopia, or like the Berenstein Bears would spell differently. It's like those the Mandela effect or something. I just can't believe I was staring at a Y or a Y the whole time.
Yeah.
That's awesome.
Yeah, that's you would not believe how many bugs are just something like that. That's why I think we did this off stream, but yeah, I actually got Daniel to send me the his source code. I'm like, I hope he's got a Y there, because otherwise it's going to be a really short debugging session.
Awesome.
All right, let's shut this one down. Thank you for watching, everyone.